So we have reached the final type of physics when it comes to particles. And this type is called fluid. It makes liquid like this. So let's get into Blender right now. And if you don't have it already, download Intro Fluid so you can get this container here and so that we can work together. Right now we don't have a particle system in here, so we have to create one. Select the plane and then go to Particle Properties, press the plus sign, and now we can do some changes. I will change the lifetime to 1000 so we don't get any particles killed during animation. Then I will go down until I find physics, and I will change Newtonian into fluid. Then I will go down again to render and change render as to object, and the object will be our particle, and then we have everything settled here. We don't do these changes on any parameter for the fluid right now. I just go and start the animation. And now when I start animation, I can go forward a few frames and then stop here. In the basic settings, fluid particle behaves like Newtonian particles. So they are sensitive to gravity, internal and external forces. So like if you're putting in a force, it will affect how the fluid particles are spread. Then we have like an extra layer at top that makes this fluid particle, and that is a math formula that is called SPH. What that letter stands for is Smooth Particle Hydrodynamics, and that is a way to calculate how one particle will move and also how it should react on all the other particles that are neighbors to that first particle. So if we look at this animation here, you can see that it have like clusters or groups or particles. So what this SPH is doing is that it looks at the neighbors and depending on the parameters does what it should decide to do. Example that, okay, I will try to glue these together, or if it's too far away, or if the liquid should be a type like mercury, then the particle tries to push the neighbors apart from each other. So it's very much depending on what type of parameters you put in. So if using pressure, velocity or repulsion, you will get a liquid life into those particles. Now if I continue the animation, you'll see that it's now connecting like a puddle of liquid here. You can also see when particles are reacting with these big things here, the edges will move on the side even if the particle is coming from that side. The pressure and velocity from here will make everything move, so it makes a liquid simulation. You can see the edges moving. Now all liquid is collected here in this case. Then it's just pouring down like this, and it's draining out from that little hole, and finally it's collecting on the floor. And that is how it works. And to make it work in different ways, you have of course some parameters. So let's look at them now. Select the plane here and go to the particle properties and then go down to physics. And here we have a few parameters. More than a few. We have a lot of parameters. But since this is just an introduction to fluid, I will not go through everything in this session. I start with the solver. Then default is a double density. And my suggestion is that you keep double density. You have something called classical, and classical is more accurate and work exactly as it should in reality, but it has some disadvantages. Because classical is much more unstable than double density. Classical also take longer and longer time, if you have a long animation, to do all the mathematics. So double density is much faster because it will not decrease the speed of the calculation even if you have a massive amount of frames, and it's not so unstable. And you can see the difference here. If I go to classical now and go back to frame 1 again, I have not changed any parameters, I just changed to classical and then run the animation. You can see that everything is just crazy. Everything is crazy because we have two big parameters, so the weight of the particles are wrong and so on. So we have to do some adjustments to make this classical work. The problem here is when we change those and then you go back to double density, it will not be the same type of parameters or values to make double density work. So you have to select the type of solver to work with from start, or you would have a really big headache in the end. My suggestion, as I said from the beginning, is to stick to double density. It will be so much easier for you because everything will then just flow as easy as the liquid here. So that is double density. The meaning of the phrase double density, if you want to know, because I've seen questions on forums and no documentation about it on Blender, it's that every particle starts with two densities. So you have one density that is the actual density on the particle, and then you have like a second density called near density, which is like an approximation on where the particle will be and what type of density it should have in the next frame. So that is why it's called double density. It has two calculations when it comes to density. So now you know it, just some fact, and you can forget it again if you want to. Then we look at stiffness. Stiffness is how eager the particles are to be together. So if you have like a high stiffness, they create these small groups, and if you have a low stiffness, then they create fewer but bigger groups of particles. So that is stiffness, and I can show you the difference here. If you have no stiffness at all, it's pouring down like this. Almost like Newtonian, because you can't see that it groups at all. It's just flowing down to here, so nothing happens in this case. If you instead use a high amount of stiffness, you will see that it will be these small groups. So I think I changed stiffness to around 5, and then I run this again, and now you can see it's more like jumping around. It's trying to find a good partner to be with and create small groups like this. Now it's more like Mercury. It's unstable but trying to form things, and you get a complete different pattern. So it's good when you have this type of liquid where you form small types of groups, or that it will not stick to the ground. Then you use a high amount of stiffness. I can take down the stiffness a bit so you can see how everything else works. Next thing will be like viscosity. Viscosity changes how the liquid will pull down the slope. So if you have a high viscosity in a liquid, it's like honey or oil or something similar like that. If you have low viscosity, then it's a thinner type of liquid like water. However, in the physics here in Blender, they have turned that around. So low viscosity gives things as oil or honey, and the high viscosity is more like water. The viscosity is also very much depending on the weight of the particles. So let's put viscosity to 0 and run the animation to see what happens. Now we have it here, and it flows down and it looks like this. You can see some movement here that is a bit unstable, Then I think we can take up the viscosity a bit. Let's see if we can find it. Down, and I put it to like 10. Now I run the animation again. However, you will not see so much of a difference here. It's a little bit calmer, but not so much. So nothing happens when I do viscosity right now. And that is because of the current mass value. So let's change the mass value. Start with checking multiply mass with size and put the value to 100. Then run the animation. We have still a viscosity of 10. And if I now select the plane and go back again, take down the viscosity to 0 and run again, you can see now that it's more pouring in small rows here and moves in a bit different pattern. But in reality, it's very rare that you use viscosity to slow the water down because, as I said, it's much depending on the mass. But it's also so that very little happens regardless if you're using high or low viscosity, if you don't get all the parameters completely correct. So I normally don't use viscosity so much. If I want something to go really slow, then I go to integration. And there we can change the time step for the integration here. So if I take down that to 0.2 and then run the animation, you can see that it's going much, much slower now. So it's more like honey that does not have a fast flow. So it takes some time for it to get through here. So you can use the time step to increase or decrease the speed of everything here. And then you also have adaptive in the integration. And adaptive is an automatic way to add subframes. Subframes in Blender is used to make calculations between every frame to get a more stable simulation. So you can take up the subframes, but that will also slow down the animation as I showed you before, or you can check adaptive and keep the subframes to 0, and when you do that it will control so all the calculations are working and that nothing is going crazy, and if it's starting to get crazy then it automatically adds some subframes during that period until it has settled down again. So use adaptive instead of putting a fixed amount of subframes if you don't have a specific purpose of just putting those subframes in. And that is what this integration does. It controls all the simulations in a good way. Okay. What I will do now is change the particle size. So I go to render and I change the scale randomness to like 0.5. Then I go back to frame 1 again and run the animation so you can see that we have different sizes on the particles. Then I go up and show you the last thing that we have on physics if we don't care about advanced, and that is buoyancy. Buoyancy is a force that makes things float, and it works almost as, like I could say, anti-gravitation. So if I increase the value for buoyancy and run the animation, you can see that not so much is happening. Let's increase it even more. And then we run the animation again. And then you can see that now some of the particles leave the ground while others are still on the ground. And that is because the particles with low pressure and low weight will more easily be affected by the buoyancy. So they go up and lose the gravity, and then they reach the sky. So you can use the buoyancy if you are pretending that this is like air bubbles or using different types of liquid. It's just to play with the value of buoyancy. If you want some on the ground, then keep it about 0.5. But if you want all particles to reach the sky, then just change them to maximum or 1, and most of them will then leave the ground, as you can see. That is how buoyancy works. That is the different things in physics that you can change. And as I said earlier, the mass matter a lot when you're working with fluid. And there is also one thing with the particle source. Even if you want small particles in your simulation, like I use like a scale here of, see if I can find it, 0.005, then you should still keep the particle source rather big. Because if you have small particle source, it will be more unstable simulation, even if the end size is the same. So it's better to have a big source object as a particle and then scale it down in the particle properties, instead of having a small source with a bigger scale, because that would make everything unstable and you will have a hard time doing the simulations here. If you go all into advanced settings, there you have things like repulsion, factors, stiff viscosity, interaction radius, rest density. You can do a lot of stuff to reduce the instability and make things more stable. But then you are in like infinity amounts of parameter settings, because they are all interacting together with each other. So changes of the mass will interact with repulsion factor, the stiff viscosity, interaction radius, and what you put in as a value for stiff viscosity will interact with the repulsion factor. Yeah, you get the point. You get a lot of dependency between these parameters, and it can take a long time to get everything exactly as you want to. So the conclusion is, if you just want some fluid, then just use the new MantaFlow. What I can mention before I finish this session is that SPH, which is the math formula that Blender works with to make this happen, and what I mentioned before, that is completely, meshless. That means that each particle has its own pattern. It's not depending on other particles, but it also means that you don't get a good surface. It's always scattered particles, so no surface that you could have as the surface of the liquid. You can do things about that, and one is to use metaballs that is included in Blender. And I will also go through metaballs later on. But there is also an add-on that you can use. That add-on, I think it's called Cube Surfer. And it's something that a company or person called PyroEvil developed for Blender until version 2.79. Then it was transferred to a new version of Blender by another guy, a girl called Porkminer. However, it's still a bit unstable, so you have to do some workarounds to use that add-on, but you can also look at this YouTube tutorial. This one, it's not mine, but it goes through everything and then you will see how it works. So that is one solution that if you really want to use these fluid particles, not the MantaFlow, you can use this and then still get a complete surface. So in that case, yes, then use the Cube Surfer. Okay? So this concludes everything about physics types when it comes to particles. And I just see you in the next session and say bye for now.